Hello everyone, so this is the recorded lecture for CSE100. So what I'm going to try to do here is, instead of doing two separate lectures, I'm going to try to do this all in one go. I'm not sure how much I'll be able to record of this. Maybe I'll have to do two videos because I'm running a program on this computer that has been going for literally 4 days, so I'm not sure how much I'll be able to record, but I'll try to do as much as possible. So the thing that we have been talking about for since last time is this notion of how do objects in classes relate to each other. So the first one that we have been really talking about is the one about composition, where we say that a class has another object. So, for example, for employee, one choice of composition would be that the employee has a string ID. So every employee has an ID, and so therefore the employee class owns the ID object. And so normally that would be aggregation, but in addition to that, C++ says that whenever we create an employee object, the ID object, once this employee object is created, the ID object is also created. And when the employee object is about to be destroyed, the ID object is also about to be destroyed. So when composition happens, it's because the outside class owns the lifetime of the inner object. And so the vast majority of the time, we're dealing with composition. But I mentioned in class before that sometimes you have aggregation where you don't own the lifetime of the object in the case of smart pointers. And say for shared pointer, there's a centralized resource that is controlling the lifetime of the resource that is being pointed to by all of the shared pointers. It's not the individual shared pointers that are owning the object necessarily, but an outside resource. So that would be aggregation. Composition is pretty much any other case. So like here, employee owns string ID. The normal case, that would be composition. So we saw a different type of ownership here, which is inheritance. So as I said in class, inheritance is about enforcing code reuse, is a tool for code reuse. So instead of having to write a whole bunch of code for the employee class here, and having to write it again for the professor class, I can just say that because all professors are employees, therefore I don't have to rewrite all the code for employee because all professors are employees. A professor is an employee. So whenever we have an is-a relationship between one class and another, that's inheritance. So in this case, a professor is an employee, therefore we should use inheritance. We shouldn't use aggregation or composition here because a professor doesn't own an employee, at least at ASU. So for inheritance, then, we need to have an is-a relationship. So the parent class, or the one that is being inherited from, that is the superclass, base class, parent class, all of those names. They all mean the same thing. And then the class that is inheriting from employee, in this case, is the child class or subclass or derived class. So a great question was brought up last time, which is, how come I have to say in public here? So wouldn't it make more sense if I did this instead? And that is what most other languages do, but C++ has a little bit of a difference here. And the difference lies in whether we can put public, protected, or private here. So remember, public means that anyone can see this function or attribute. Private means that only the functions inside the class can see whatever that is, either the function or the attribute. And protected means the same thing as private, but you give access to all subclasses. So for the ID here, the professor class, because this is private, won't have direct access to this because it is not protected. If I instead said put a protected label here, then the professor class would have access to it. So what is the rule for what should go here for the public employee? Should I put protected here, or should I say private here? So what happens, actually I made a mistake, sorry. So when I said that this is private and then therefore the professor class doesn't have access to it, that's not actually true. So it actually depends on what the modifier is here, whether it's public, protected, or private. So what is the rule? So the rule is, if you have public inheritance, then the visibility in the parent class stays exactly the same. So if it was public before, it stays public. If it's protected before, it stays protected. If it's private, it stays private. For protected inheritance, so if I did this instead, then what will happen? Then what will happen is, if it's private in the base class, it stays private. If it's protected up here, it stays protected down here. But if it's public up here, then it becomes protected here. So you may remember a function that I asked you at one point to code up called clamp, which is you're given a value and a range, and you want to clamp the value in between the range. That's kind of what's happening here. So if it's outside of the range of what protected means, whether it's private or protected, so outside of that scope means it's public, we're going to clamp it down into protected. Okay, so if I had public inheritance, nothing changes. So all the visibility inside the employee class stays exactly the same as the professor class. And if I made it protected, then the only change is that public stuff becomes protected in here. So then what about private inheritance? There, it's like clamp again, but effectively what happens is that everything becomes private. So no matter what the visibility is in employee, professor's class will have everything private. And so if you want anything public, you'll have to write something different here that is public. So if we, for example, had public inheritance here, then ID will have private visibility in here because it's private up here. And the function f here has public visibility up here, so we'll have public visibility here. If I instead said protected here, then ID will still stay private, and f now will become protected because it has public visibility. If we had private here, then both the ID and the function f will become private. And so if we make more subclasses, such as tenured professor, which is a professor, even if I put public inheritance here, then because I put private here, the visibility stays the same. So what happens is, if you do any kind of switching here from public inheritance to one of the other two, then that'll be filtered down all throughout the subclasses of professor. So you have to think about, when you're going to put a visibility modifier on your inheritance, whether or not you are thinking about your subclassers. So if you're thinking about tenured professors and whatnot. So that's why the vast majority of the time people recommend putting public on your inheritance, because you keep the visibility everywhere exactly the same. So you may notice that there is no inheritance modifier to, say, convert from the ID attribute to become, say, protected. And so this is one of the aspects of data hiding and encapsulation, which is a central tenet of object-oriented programming, which is that you want to hide by default, and if you need things to be public, then you make them public. So that's one of the reasons I think that there's no way to make things more visible, only to make things less visible. So this is the example that we have talked about in class, and inheritance of members. So we now know that the public inheritance means that the two up here, which are private, are going to stay private down here, but the child class, of course, gets everything that the parent class does. So there's sometimes some issues with dynamic allocation. Again, I didn't go over this. It's not really a big deal for what we're doing. The important thing is to understand what inheritance is. So we went over protected before, which is this third visibility modifier, which means that the subclassers can access it, but no one else can. So as an example, if we have a main function here, and I make a professor object called P, then I can call the function f on the professor because the function is public here. We have public inheritance, which means that the visibility of f stays the same, which means outside the class we have access to it. If I instead said protected here, then this won't compile because this is outside of the class. Okay, so this is where we ended last time. We can have all three kinds of inheritances, and this is what we basically just went over. Okay, if we have constructors, say in the employee class, then what happens is the derived class constructor automatically inherits the constructors as well as the destructor, but you can specify which constructor you want to actually use. We won't go over on how to exactly do that, but the point here is that no matter what you create in the parent class, the child class gets the same thing. So if you make a constructor or destructor upstairs, you get it also downstairs. And so when you make objects like this, so let's just say we leave the professor class like this, and let's just say we have the implicitly defined constructor. So we don't have to write the constructor ourselves, it's implicitly generated for us. And let's just say we have public inheritance to make everything work. So when we make this professor object, then the constructor of professor is called because we're making a professor object. But to fully construct this object, we need to defer any remaining work that is shared between professor and employee to the employee class. So what actually happens is the professor's constructor here is being called, and then once that is called, it automatically calls the employee's constructor to finish constructing all of the data that is shared between the two classes. So always what happens is that the child class, or really what the term is that this is the most specialized class. So a professor is just a specialization of employee. So here, the most specialized class is constructor is called first, and then you go up in the inheritance chain until you reach the top, and you call the constructors all the way. If we go past that and we call f here, notice that the function f is not explicitly written here inside the professor class, but it is in the employee class. So what happens is, if it can't find the function f inside the professor class, it goes up to the parent class and attempts to find whether that function f is there. If it is, then it executes it. So one interesting side effect is we could have a function g, for example, that does whatever in here, and let's just say we have a tenured professor that has public inheritance with professors, and we make a tenured professor here. So if I call g here, notice that the tenured professor class does not have G in it, but the professor class does. So what happens is that it doesn't go necessarily all the way to the top to call a function. It goes up as far as it needs to until it encounters the right function. So it can't find it here, but it does find it here, and so therefore calls it. And so that's the order of execution here. You start at the derived class, and then you go up in the hierarchy chain. And the same thing is true for the destructor. You call the destructor of the derived class, and you go up in the chain as you need to. Okay, so let's actually get on to new stuff. So let's just see the slideshow, whether it works or not. Hopefully this works. So these three topics here, hopefully we'll get to all of them. But they complete the picture, so to speak, of things that we have left so far in code. So let's just go back to some of the earlier stuff that we've done throughout the semester, such as if we have like an integer n, we see an n, and then we had some code like if n is less than 0 or something, then we see out bad input, for example. And then what we did is like return 0 to quit the program, because we don't want to proceed after this point if the user's input is bad. And so that worked fine. What if we wanted to actually communicate to the person who's writing the code, hey, you entered something bad here? And what's even more important is, what if we don't want to actually quit the program here and instead say, we're going to catch when this happens, determine when this bad input happens, and then maybe let the user figure out, okay, something went wrong, let's fix it. Or maybe if a certain error occurs, we don't want the program to crash, but instead we want to notify the user whether something went wrong. So that's what an exception is. So exceptions are basically, they're entirely objects. So they're just an object of a class, and they're just called exceptions. So there's nothing really inherently special about them, but we use them to indicate an error when it occurs. So what happens is when an exception occurs, either the program must stop or jump to special code, and we'll talk about what that special code is. The code itself is called exception handler. When an exception happens, we want to handle what happens as a result. Whether the user's input was bad or division by 0, we want to figure out, okay, what should I do at this point? Should I quit the program or do something else? So if we want to say, hey, an exception is happening here, I'm going to notify that an exception is currently going to happen, you use the throw statement. So a throw means we're throwing an exception. So the terminology is throw an exception. So what we typically do is we throw exceptions directly. So the objects themselves, we throw those. But we can actually throw anything that we want. And they're used to signal exceptions. The try block, so any code that could potentially throw an exception, you put in a try block. And we'll see how to do that. So it's kind of like an if statement, but here we're saying we're going to try to do this code, and if something happens, an exception does get thrown, we go down to catch statements. And catch statements are saying, hey, for this exception, I want you to do this. For this other exception, I want you to do this instead. If you have all these exceptions, I want you to catch all of those cases and do the same thing for all of them. But if an exception does not happen at all, then no catch statement or block is actually executed. So in code, you write a try block, and then after that, you write catch blocks. So if you want to throw an exception, you can really throw anything here. So you can throw a string or throw an integer. So this first one can seems like it does make a little bit of sense, but the second one I don't think really makes much sense. If throw 12, what does 12 mean for an exception? What does 12 mean for what kind of user input was bad or something? So what we typically do is we throw an actual exception object. So there are things called exception objects defined in the C++ library. And you throw those to indicate what kind of error actually happened, what kind of exception happened. So if we want to actually write a catch statement, you write catch here, and in the parentheses, you write the type of exception that you're going to see. So here, this catch statement says, if you throw at any point a string, doesn't matter what the string has, if you throw any string at all, then this catch statement will be executed. So in this first case, if we threw this string right here, then we'll go into this catch statement right here. So if the throw statement right here is in the try block, then we go into this catch statement. If instead we throw the 12 here, then we don't go into the catch statement because it's expecting a string here. If we had another catch statement here that corresponds to integers, then we would go into it. So these things are, of course, the exception handlers. So this is what happens. So this is for the structure of try and catch. So try goes up here. Any code that corresponds to throwing an exception goes inside there. And catching, say, a char. So if you happen to throw a character, then the catch block will be executed there. So let's see. So if we have an example like this, then a better way of doing this is to write a try block. Then let's do the cin here inside here. So then what we can say is if n is less than 0, then we can, let's just say, throw just a simple string, a bad input to keep the behavior exactly the same. So then here we need to write a catch block, and we could theoretically throw any type of string here. So that's why we're saying we're throwing some string called s, and then here we wanted to print to the user, hey, you're doing something bad. We're going to print this string s here because the string that was thrown is passed into here as an argument. So I print s, and then here I can do any work that I need to. So if I want to quit the program, I can do return 0, or as we learned before, exit 0, or whatever I need to do. And then if we have other catch blocks, we can't have two different string blocks like this because each block corresponds to any arbitrary string. So if you have two things that you want to throw and they're of the same type, and you want them to have different behavior, then you should either write a class for each of those cases or something else. Because if you throw a string here and then at some other point you throw a different string, then both of these cases will filter into this catch block, and that may not be what you want. So so if we have another different type of throw for integers, so maybe we do that weird example throw 12, then that that throw will reach this catch block instead. So it'll skip this string one if we encounter this one and not this one, and we go down here. Another thing is, if we encounter a throw like this, then the rest of the code in the try block is not executed. It's unconditionally jumped to the corresponding catch block. So if you throw at any point, think of it as like a break in a loop. You immediately exit the corresponding structure, which is the try block here. Yeah, so the catch block syntax is like a function. The block has the parameter that we just talked about. An exception, of course, could be like computing the square root of a number. So like our example, if they enter an input that's less than 0, then that's not a valid input for the square root. And so therefore we could throw the error and then maybe quit the program or whatever we deem reasonable to do. So this is the example that they give. So we have a double here. If we input the double, if it's less than 0, we throw the string. And remember, if we have a throw at any point, we immediately exit the try block and then go into the catch block. So the square root part of it will not be encountered because if we encounter the throw statement here. So, but if we have a good input, so this statement is not valid, this statement is false, we don't encounter the throw statement, and so that we proceed on the square root. So it's filtering out the errors that might actually happen. And you may have noticed this CERR thing. So this is actually the third type of input-output. We've seen Cout and Cin. CERR is outputting, but whenever you have an error. So if you want to communicate to the user via output, hey, you're doing something bad here, CERR is a good way to go, not Cout. So Cout means you're printing normal output. CERR means you're outputting possibly error-prone, output that the user should interpret as an error. Okay, so if you encounter a throw statement, you immediately get out of the try block and you go to the corresponding catch block. Okay, what if you forget to have the corresponding catch block or just don't have any catch blocks at all? The program will stop no matter what happens there. So if you don't get the exception gracefully, so you don't catch the exception, then the program will stop. And it seems like a good idea, in my opinion. If you are not handling the exception, then something is inherently wrong with the current state of the program, and so there's no reason why the program should continue. So terminating is a good idea here. Unfortunately, what I've seen programmers do sometimes is let's just say we have one catch block here. And what happens here is we leave the catch block empty, or maybe we just have a Cout statement here, or CERR in this case, but we don't actually handle the input correctly. So maybe we have, like, say, this square root idea that from the example that they give. And so what will happen here is if the input is less than 0, and then we encounter this catch block, so maybe we'll get rid of this one. We encounter this catch block, but n still has a value less than 0. So the flow here is wrong because the value n still has an invalid input. So what people should do is inside the catch block, maybe go to a different point in the program and have the user input a value again, or enforce that n is at least 0, so maybe if it's negative, set it to be 0. There are a lot of things that you can actually do here. But if you don't have the catch block at all, and we encounter a throw statement without a corresponding catch block, the program will stop. But of course we can have multiple exceptions, as I've said. We can have a catch for integers, strings, doubles, or really any type that you want. As long as you throw the corresponding type, it'll go to that catch block. But more common is people using exception classes. So instead of throwing a particular string, people throw an object of some exception class, and we'll see an example of this. And the reason for that is that the class will have a lot of useful information about what actually occurred, such as what is the error string that you want to communicate to the user, things like that. And it's wrapped up nicely in an object, so you don't have to worry about whether it's a string or whatever. And the purpose of the classes is to communicate what type of error actually occurred. So let's see. So do we have an example in here? No, we do not. So let's actually look up an example of this. So let's look up exception classes C++. So the main class that people inherit from, so this is getting back to inheritance. All exception classes are of type exception in the standard library. And all different types of exceptions inherit from this exception. Or if you want to make your own custom exception for your application, then you should inherit from exceptions so you don't have to rewrite a whole bunch of code again. So a lot of different types of errors are here. So what is very common is something called a domain error. So like for square root, if you have a negative value, then a domain error might occur because it's outside the domain of the square root function. Or in the case of vector, or in fact string, if we use the .at method of vector, then that will throw an exception if you go outside the range of the vector, which is nice. So you may get an out of range error and things like that. So here's an example. So here, ignore what this is actually doing. This is something called polymorphism, which we'll not talk about in this class, sadly. But the key here is we're throwing some exception here. So it happens to be something called bad type ID. You don't need to know what type ID is. But the point here is that this catch block corresponds to the general exception here. So if you want to handle all possible exceptions all in one catch block, then this is the way to go. And they pass by reference here because the exception could be very large in size. So what is recommended here is not doing this because unless you are handling all exceptions at once. If you want to handle all exceptions at once, this is an awesome idea. But if you have different types of things that can go wrong, like a domain error or an overflow error, saying there's an error that occurred, there's an exception that occurred, just an arbitrary exception, that might not be useful. But if you say in the case of domain error, hey, you entered a value that's wrong, or in the case of, say, overflow error, you entered a value that's too big, or the value became too big in this case, then that will be more useful. So in the general exception case, they have a function called what. And I love the name. It's absolutely perfect for this. So let's see, where is the what method? Let's see. Is it in here? Maybe it is. Maybe it isn't. Oh, it's right at the top. Okay. Ignore the virtual up here. That has to do with the thing called polymorphism, which I talked about. So it says returns a null terminated character sequence. You can think of that as a string that can be used to identify the exception. So here, this will communicate what the exception is. So in fact, here is a custom exception called oops. So here we're inheriting from exception. By the way, notice that there's no public here. This is a public inheritance by default. So if you want to have public inheritance, just leave the public out. But it's clearer if you write public here. But anyway, the standard exception class, the function what, if you're going to write a custom exception, you need to write what does this exception mean. So if we have a custom exception, say for this example, like the integer less than 0, so actually let's do this. So let's actually write our own custom exception. Could be kind of fun. So ignore the fact that it's a struct. Let's just make a class for this. So let's call it less 0 exception, which inherits from standard exception. I don't need the standard colons. And of course I need to inherit from exception. Okay, so here I need to return a const char star what, because I'm redefining what this function does. If I didn't redefine this, then it will look up into the parent like we have talked about before, and it'll do whatever the exception class says to do. Ignore the const no except here. It won't actually make a difference here. So here we can say maybe let's do the same error, but I don't think this is actually very good. So maybe we'll make this a little better and say input was less than 0, for example. And then here, what we'll do is we'll, instead of throwing a string, do a better exception here and throw the less than 0 exception. And here, when we do the catch, we can do a standard exception here without the standard colon because we don't need it. And then we can print out x dot what. So hopefully this works. So let's actually try doing this. So let's compile our video lecture and then a.out. So if I enter, say 7, it actually didn't do anything, which is exactly what we want. So let's actually make this clearer. So maybe we'll print square root of n here. I'll ignore the fact that it's an integer, just purely for the sake of demo. Use of undeclared identifier square root. Okay. I think I may need to include a different header for this. I don't remember the header offhand. Okay, so this is why you don't try to memorize functions, because they are in different headers. Yeah, C math. Funny how I taught this and I forgot. So let's see. It's 8:53 p.m. and I am tired. So let's actually run this. So let's run 7 again, and it gets 2.64, which is square root of 7. If we do 0, it gets 0. If we do -1, then, okay, that's weird. That's weird. So let's see. We threw the exception. Let's see. Do I need the const no except in here? Let's see. I don't think I need to. So the const here is something different than the const here. This const says I'm not modifying the exception, and the no except means that this code inside here is not going to throw an exception. But that shouldn't have any issue. Let's see. Because I inherited directly. So let's see. Is more lax than... Maybe I need a struct? Oh, I need to make this public, I think. Or not. Let's see. So what was the error? Expected this. Do I need a higher version? Okay. So the const actually had something to do with it. So hopefully this works. Oh, okay. Well, let's see. So let's see. So we threw the less than 0 exception. Maybe we need to actually have a less 0 exception in there directly. Okay, so I guess this example is wrong, because what happens here is for some reason it didn't call the exceptions what method, but instead it deferred to our own one. Maybe, did I spell it right? Yeah, I spelled it right. Huh, that's weird. So that's one of the reasons why I heavily recommend that you make your exceptions as precise as possible. So instead of dealing with general exceptions, work with the most specific one you possibly can, which is less 0 exception in our case. Let's close the other slides and let's get to new stuff. So if you can't allocate new memory, maybe we allocated so much memory that the computer ran out of memory, then a different exception will occur, which is badaleck. So For some reason, if the new if new can't allocate memory, then it throws this exception. If you're allocating a ton of memory, maybe you're working with big images, then you may want to actually consider this. But memory is so big nowadays that you never will encounter this. And if you never use new, you don't have to worry about this anyway, because this only occurs when you encounter new. Because remember, new is associated with dynamic memory. If you have static memory, you won't have to actually worry about this because of other reasons. Because for static allocation, the compiler knows exactly how much memory you're going to be allocating. Whereas with new, since it's runtime, you don't know necessarily how much memory you're going to allocate. So the compiler can't figure out whether or not you're going to use too much memory. Yeah, so the compiler tries to figure out the suitable handler. If there's no matching handler, it terminates execution and continues to search. This is something that I won't actually test on, but it's something to keep in mind. So if you're very deep in a function call, so like one function calls another, calls another, calls another, calls another, calls another, and then that last one throws an exception, then what happens is called unwinding the stack. So what happens is if we have a function A called a function B, called a function C, called a function D, and D throws an exception, then what happens is it unwinds the stack. It goes up to C, does anything try catch related in there. If it can't find any, then it goes up to B, then it goes up to A if needed. So it unwinds its way up to the stack until it finds the corresponding try catch block. Or it goes all the way to main and it quits the program because it can't actually find it. So we usually don't worry about this, but sometimes you will have exceptions flowing through your code. Even though you're not throwing exceptions directly, sometimes exceptions can flow through your code. So maybe a function that you call will throw an exception, but it will pass through you because you're not responsible for handling the error. So just knowing that exceptions can flow through can be important. So let's get on to a new topic. So one of the issues with writing functions is that so far we had to write functions that are specialized to a given type. So for example, if we wanted to write a swap function which swapped the values of two variables, so we take them by reference and swap them with the temporary here, we've seen how to do this. If we wanted to do one with integers and we wanted to also do one with characters, we have to write two different functions. But notice, look at on the inside of the functions and the return type and the actually the names of the variables themselves. The only difference between the two is the type. So notice here that it takes an integer by reference, but notice that it's just an integer, and then the temporary on the inside is an integer. Whereas here, they change in the same way. So the integers get swapped to chars. If I did the same thing with strings, I would put strings here. If I put vectors here, I would do vector. So no matter what type I consider, I can put any type here as long as I put the same type for y and the same type for temp, then all of those work. But the problem is, what if I wanted to swap user-defined types that are not known in advance to me? I can't write this swap function for them because I don't know what their type is going to be. So a function template is basically like a blueprint for a house. We have a specific set of instructions which works in the general case. But if we wanted to specialize it further, then we can specialize further. But if we want to just work with what is given to us in the blueprint, then that'll be good enough. And the good thing is, with blueprints, we can put the house anywhere we want. It doesn't matter. As long as we follow the blueprint, everything works fine. So that's the same thing here. A function template is basically just writing a function with a type that it can be arbitrary. And if I want to call the function with some arbitrary type, then I just call it with the type that I want, and it'll specialize all the code for me. So how do you actually do this? It's super, super, super easy, and it's super powerful. Enough supers? So here's how you do it. Before the function begins, so actually before the return type, you write template with angle brackets and class, and then the name of the general type. So here, you can think of t as int or double or whatever. But t here just means general type. The t can be anything I want. So in fact, what I can do is I can just say general type like this, and as long as I keep that type consistent across the implementation of this function, I can put anything I want there. But the convention is to use t because t corresponds to type. So here, if I wanted to call swap with integers, then I can just call it with integers. If I wanted to call it with doubles, I can call it with doubles. I only have to write one version of the swap function, and everything else will carry through. I don't have to worry about anything else. As long as I can write one version of the function, then everything else carries through, which is amazing. So, and notice, I don't even have to specify which version of swap I want to call. I don't have to specify what t is here. I can just call the function with the arguments, which is pretty amazing. And what could be even cooler is, notice the swap right here. It says, I can take an argument of type t, by reference. I can take another argument of the same type here. What if I wanted to be able to swap two variables of possibly different types? Then what we can do is put a comma-separated list here with two types, and I can put u here, and so the t has to go here because I'm assigning x to t, and as long as the type of t can be assigned to the type of u, then everything else carries through. So what actually happens here is something called template argument type deduction. So the template here, the t and the u, those are arbitrary types. I'm passing integers along. So in the function template, t is deduced to be an int because the first argument passed in was an int, and the second one is deduced to be an int because the second one is also passed in to be an int. What is even more amazing is that the code will only write into the executable the necessary code here. So it doesn't write out, hey, here's a general template, and you can call it with a specialized arguments, with ints or with strings or whatever. It only creates, if this is the only time we call swap right here, then the only code that's generated for the function is for the integer version, not a general type version. So, which is pretty awesome. So if we called swap in addition to this with two strings, then it'll have in the executable one version for integers and one version for strings. And it'll automatically differentiate between the two, which is pretty cool. So yeah, so it's templates are patterns. No actual code is generated at all until the function is called. So if you have a function template and you don't call it, no code's generated, which is cool. The template itself uses no memory in addition to, let's just say we call it, no additional memory compared to just calling the function normally. When you pass a class object to a function template, make sure that all operators are overloaded. So what that means is that, so let's actually copy the example that we had over. And maybe let's make it go back to the T version. I'll leave it indented like this. So let's convert it back to the single template one and then have T be here. So if I have a custom type here, we better make sure that the equals operator works, the assignment operator works here, from assigning from a T to another T. So this won't actually work, say, with unique pointers, because unique pointers, you have to call the function move for this to be able to work. So you have to be careful to make sure that the T's here can have the assignment operator, in this case, overloaded. If it doesn't, then it'll throw a compiler error at you, and the compiler will be mad at you for that. So just be sure that you overload all the relevant operators here. If we have the plus in here, or we're printing the argument of type T out, or something like that, we got to make sure all the operators are correctly overloaded, which is something that we talked about before. Okay, so yeah, we talked about that. If you have a template prefix, so the T and the U thing that we talked about, those are the template prefixes. All data types you make must be used somewhere, which is pretty obvious. When you call the function, you must pass parameters for all data types specified in the prefix, which makes sense. So if you specify you're passing a T and a U, you better pass a T and a U. Or it's not necessarily different types here, but rather you're specifying a type for it. Templates can be overloaded. So you can have a template which has two template arguments, so the T and the U, or we can just have a T version, or both actually. They could be overloaded like this. Like regular functions, function templates must be defined before being called, which is obvious, because they're just functions in reality. So when to use templates? We don't typically use templates. So the primary reason why I use templates is actually not to say I have multiple versions of a function I want to call and I only want to maintain one version. The main reason why I do it, and let's see if I actually have the code for it. Let's see. I have it somewhere. Density, where are we? Do I have it? Yes, I do, I think. I'm trying to open it. Opening, Sublime Text. Okay, yeah. So here's actually some of my research code, and yes, it is horrible. So notice the template at the top. And so ignore this part right here. It's not actually relevant. Here I have a template which takes a type named T, and notice that there's a bunch of T's everywhere. So there are two T's here in the constructor. The type of the vector here is T. There are T's down here. I have data types of type T, another vector of type T. So I have a vector here, but notice I said int here, well, equals int here. So why do I do that? The reason is mainly for performance. So it's more performant if your data is smaller. So if I can ensure that the variables k and t are going to be small, then I can use a smaller data type for them. And if I use a smaller data type, then it turns out that that is much more performant than if the data is larger. So if the int here is 4 bytes, if I change this to short, then shorts are 2 bytes. And so therefore, the data that's used by this class right here is twice as small. Well, not twice as small, but all of the things involving the type name t, those things are twice as small because shorts are half the size of integers. So by controlling this parameter right here, I can make my programs faster or smaller or slower. Well, I don't really want them slower, but sometimes I have to, say if the k or the t parameters here are quite large. So, and I can't handle, if k is too big and it's beyond the range of short, then I can't necessarily do anything about that other than going all the way up to int. And so my program is, in some cases, say 30% slower than otherwise. So the point here is, let's bring it back. The point here is that I can keep the change that I make consistent throughout the class. So instead of having a bunch of ints everywhere and having to change them to shorts whenever I want the data type to be smaller, that just by changing it in one place, then everything else is updated accordingly. And by saying equals int here, then I don't actually have to specify what t I want here. So that's actually how vector works. So if you look at the class vector, so let's just familiarize ourselves here. So the vector class, I'm of course not going to do all of the stuff in here, the class vector, but the vector class is actually a templated type. The template here is the vector of ints that we've been talking about, or vector or whatever. So if we have a vector of ints here, then the thing inside the angle brackets is the type name t, the class t here. So, and then you may think, okay, well, how come you have to put the angle bracket t thing here, but you didn't have to do it here? The key is here that for the functions, it can actually deduce what the types of the arguments are going to be. Whereas here, for vector, it can't necessarily know what those are in advance. Because here, when we have the vector down here, it's not initialized to anything. So it can't necessarily know, if I just did this, what the vector's type actually is. So here I have to explicitly say int here, or string, or whatever. Whereas here, with the swap function, it knows that it's getting two integers. So it's going to initialize the parameters accordingly. So, so where are we? Yeah, so when you use templates, I use it for performance, but the vast majority of the time is when you have something like something called a container. So a container is basically just a container of a whole bunch of objects of a certain type, of an arbitrary type. So vectors can hold anything, which is why the template is here. Yeah, you may have noticed that I have a type name in my research file that I showed you and a class here. They're actually the same thing. As long as you use C++ 11 or greater, you can use type name. Class is another way you can do it. They do the exact same thing, so there's not really much difference between them. So of course, as I just showed you, you can do this on classes too. So if we have a joiner class, which has a combine function in both of them, which both take two arguments, and it returns the first argument plus the second, then of course we can do a template on them to make everything a lot easier. So we can do template class t. It returns a t because it's a t plus another t, and so t is there. And so if I just wrote joiner without the angle brackets, it doesn't know necessarily which combine it's going to actually do. So here you put double. But what if you wanted a default type? So if you don't specify it here, just assume it's automatically integers, for example. Then what you can do is the thing I showed you, which is the t equals int thing. So unless you specify otherwise, the t here is going to be int, which is nice for my research because I don't even need to go back to the class. I can just change the declaration of the joiner object to double or anything I want. So here, the joiner here is corresponding to int because now the default type is int. But if I specify otherwise, the type gets overridden with double. And of course it does the result that we expect. There's a little bit of an issue if you have a function outside of a class. The issue there is normally what we would do before we had templates is we would have something like this, ignore the t's. We would have the class name, colon, the function name, and then everything else. Here you have to actually specify the template of the joiner that you're corresponding to is the same one that is corresponding to the function. So in fact, the joiner of double and the joiner of string are in fact two different classes. They're not the same class. So here we're saying if we said double for the T here, we're corresponding to joiner of double. If I instead said string here, and I set double in here, then for some reason now we're considering the string version of joiner, not the double. Here, it self-adapts in the right way. If we have T being a double here, it calls the right one, namely in joiner of double. Okay, you can do the same thing with inheritance, but there's a lot of issues there. So I'm not going to really go into this. Just note that if you have a template in the base class, you can have different combinations. So if you have a template in the base class, you don't have to specify the template in the derived classes, but if you have one in the derived classes, that's not the same thing as in the parent class, so in the base class. So the typical idea is to templatize the base class and then use the same template throughout the rest of the child classes. But in fact, most of the time we're not going to deal with templatizing classes like this because they're used for when you want arbitrary types, and those correspond to either dealing with an argument of an arbitrary type or holding an argument of an arbitrary type, which gets to things called containers. So containers in the standard library are things that can hold arbitrary objects. So the one that we've been talking about so far for a long time is vector. So vector can hold an arbitrary sized array of an arbitrary type. And you may notice these other ones. So an array, if we look at that, that's actually just basically a static array, but it's an object wrapper around it. So you don't need to do int a new or delete or whatever. It's a fixed size array. And if we actually look at the template type here, it says class T, so that could be arbitrary type like we just talked about. But notice size Tn. So think of size T as an int. It's not really an int, but you can think of it as that. So here you can actually say not just an arbitrary type, you can pass in anything. You can pass in any value you want. So if we wanted to make this array right here, this standard array, we would say, okay, we want this array to be of ints, and then we provide the size of the array. So in this case, this array is non-resizable, so just like a normal array. So we're providing the type here and the size of the array here. So if we look at let's actually look at an example of this. Is there an example? What's a good example? Let's look at size. So if we look at this example right here, we're making an array, and the type is int, and there are 5 things in there. So you can actually have templates of many different arguments, and they don't have to be types. They can be just pure values. And I actually use that in my research a lot sometimes. I had a template once where it had 4 values and no types as its argument. So that's actually, so it's not just types here. It can be values as well. But there are other things that you can have here. So like a deck, for example. So it's not a DQ, it's a deck. So deck stands for arbitrary, my goodness. It stands for doubly ended queue. So I'm not going to go into much detail about this. So think of a normal queue. So if we have the front of a queue right here, so the equals means the actual queue, and here's the back. So let's just say that we're at a bank, and here's the queue. The front gets serviced by a new teller. So we're taking things off the front, and if a new person comes into the bank, they have to go through the back of the line because we don't want people crowding at the front. And then if a new person gets serviced, they get taken off the front, and if a new person comes in, the back gets another person. So doubly ended queue is where you can have something like this, but the front and the end can extend in both directions. So you can put things on the front, or you can take things off the back. Either way, you can do this. So look at the template here. It says it's an arbitrary class T, and something that is default initialized. So some other arbitrary class that is initialized to some type. So you don't need to know what that actually does. It corresponds to, if I want to allocate objects in a certain way, then I would do this. But here, just notice it's an arbitrary type. The list and forward list are basically just arrays, but you can only traverse them either, in the case of list, both directions, or forward list, which is one direction. I heavily don't recommend you look at these two, because they're much less efficient than these three. But for some algorithms, these two are actually needed. There are other containers. So a queue is what we talked about before. Something called a priority queue, we won't get into that. A stack is where you have a different data structure. So think of a stack of plates. So think of, instead of a front and a back, think of a stack of plates. Maybe I'll do them by vertical bars to make them look like plates. So let's just say here's the top, here's the bottom. If you want to have access to a plate, the only way that I can access a plate is via the top. I can't take a plate out of the middle and take it out, or even at the bottom, because all of these plates are on top of it. So if I want, say, this plate in the middle right here, what I have to do is I have to take plates one at a time off the top. And so that's what a stack is. It's a stack of something. So if we look at stacks, the type that is in here is of class T. And so here again, here's a different argument. I didn't actually know this was here. So what I'm guessing this second argument is, just by the name of it, is how the stack is actually implemented. Because you can actually implement stack in a number of ways. But a stack is just basically, you can put things onto the top of the stack or take things off of the top of the stack. Whereas with a queue, so this is a stack. With a queue, you have a front and an end, where you can only take things off at the front, so the same thing as a stack. But with a queue, the only way you can add things is by pushing them onto the end. Whereas with a stack, the only way you can add things is on the top. So stacks are actually called last in, first out, or first in, last out. So they're equivalent. So if we had an empty stack here, and we pushed something in first, maybe not there, push something in, then we push more things. If I wanted this one out, then I need to take all of these other things off of the stack before I can actually access this one. If I put in some new plate, which is last into the stack, is also the first one that's out of the stack. And as you might expect, a queue is a LILO or FIFO data structure. So here it's the first in, first out. So the first person in the queue, of course, is the first person out of the queue. The queue preserves the order of the individuals that enter the queue. And the person who's last into the queue is, of course, last out of the queue. Okay, some other containers which are pretty useful. Map is actually pretty interesting. So a map is just an association between keys and values. So you actually saw this on assignment 6, where you had I suggested as a hint, where you had each letter correspond to a single timer. And so a map was a good data structure for this, because each key, which is each of the characters, corresponds to one value. So notice, look at the template here. It has 4 template arguments here, 2 of which are default initialized. And so therefore, you can reasonably assume that the other 2 are one's for the key and the other one's for the value. So you can have an arbitrary association of any type to any other type. So notice, just because I called it key or just because I called it t doesn't mean anything. They can be arbitrary types here. So I can have a string and a double here, so I'm associating one string with one double, that sort of thing. Another container which is really useful that I use all the time is sets. So it's kind of like a map. So maps keys are unique. So I can't have 2 keys which are duplicates in a map, which kind of makes sense. If you have a house and you have keys to the house and you want to keep it secure, you don't want duplicate keys. So that's obviously what's happening here. So with sets, you throw away the value part. It's just the keys. And even though it says T here, it really is the key type. And you can actually kind of see it here. So sets are basically just the keys in the map. It's just a collection of distinct items. So notice that there are 3 arguments, one of which is not default initialized. So those are just some, that's just an introduction to some containers in the C++ library. There are other versions for other situations, but the basic ones are array vector deck, stacks and queues, sets and maps. They all have different advantages and disadvantages. They're not all created equal. So, in fact, we talked about a lot of this. So, let's see how much we can actually get to. So, the standard template library is just the library that you've been using this whole time. It's just a giant library with a bunch of templates in it. So, vector, array, deck, queue, stack, map, sets, all of those things are templated, as we have seen. So it's a library containing templates for frequently used data structures and algorithms. So a lot of algorithms in the library are also templated, and we can actually see them if we go to the algorithm header. So let's go to algorithm C++ as the header. So let's just look at a particular example. So let's say we wanted to look at the all of function. So the all of function's purpose is it has a predicate which corresponds to whether the predicate is true for each of the elements. If all of the elements are true in the range, say in the vector, then we return true. If any of them are false, we return false. So notice the type here, the template here. It says that it takes an input iterator. So notice, because it's called this doesn't mean anything. It can be any type at all. And it takes a unary predicate. Again, it could be any type. So it takes an input iterator, whatever type that is, and an input iterator of the same type, and a predicate of an arbitrary type. So algorithms can also be templated. And they can work with arbitrary types, which is pretty awesome. So what are the data structures in the library? Containers, which we've talked about in depth, and things called iterators. So when you call sort or all of or whatever function with, say, a vector.begin or in vector.end, what happens is those things are iterators. And so they're like pointers, but they provide ways of accessing things in a container. So we kind of went over all of this already, so we don't need to talk about this. Yeah, we don't need to talk about this. So let's get on to actual iterators. So they're just like pointers, but they can have a whole bunch of amazing things that you can do in addition. So there are different types of iterators. Forward ones, bidirectional, and random access. And even other ones, which we can talk about. But the two main ones are actually, the first three are the main ones that are used throughout the standard library. So let's actually think about this. So for all of, what type of iterator do you need? How should you access the elements in an iterator? Well, the way that you should access it is, well, does it really matter what way I access the elements? And the answer is no. It doesn't matter how I access the element. So we might as well just use the iterator that is the least restrictive. So random access is the most restrictive. Bidirectional is less restrictive, and forward is even less restrictive. So every random access iterator can be a bidirectional iterator, and every bidirectional iterator can be just a forward iterator. Sorry, the other way around. Every forward iterator, actually no, I had it right. Every random access iterator is a bidirectional one, because I don't have to use random access here. I can just access the elements bidirectionally by going forward one position or back one position. And every bidirectional one is a forward one, because I don't have to go backwards with the iterator. I can just move forward as I need to. So if I can use forward, I might as well use forward. Why should I always use forward if I can? The reason is, if you are so unfortunate to deal with structures that like forward list, which only have forward iterators, then you want to be able to have your algorithm work for that iterator if you can. So, but if you require, say, random access through the data structure, then you can't, of course, use forward list, because that requires that you use only forward iterators. You can't use any other iterator for forward list. So for all of, we don't need anything special here. You just need to go from the beginning to the end. And actually the same thing is true for most of these algorithms. But one notable exception is sort. So for sort, because we need to be able to access arbitrary elements for sort, we need to use random access iterators. So if you have a data structure that uses bidirectional iterators, it won't work with sorts here. But think of, say, bubble sort. What happens here is, because bubble sort moves through the data structure through passes, it doesn't randomly access elements of the data structure of the vector. For bubble sort, we can in fact use forward iterators, because we don't need to move backwards in the iterator here. We only need to move forwards. So different algorithms can use different data structures. So for forward list, one of the neatest ways of using sort there is by using bubble sort. So depending on what data structure you have, sometimes you can't use one of the functions in the standard library. You need to be able to think, what data structure should I use, and what function should I use in this situation? Okay, so if you want to have access to iterators, you can use it like this. I won't test this because this is just old style way of doing things. You don't actually need to do it this way. But the way that you find out the iterators is usually by calling .begin or .end of a vector, and that'll give you an iterator. So when you call sort, say, with the begin of a vector and the end of a vector, you're really just passing the iterators along. And so therefore, the sort, and for vector, we have random access because we have the square bracket operator. We can just access any arbitrary element that we want. So therefore, for that reason, we can just pass in the begin and the end of a vector, and everything works fine for sort, which is kind of awesome. But iterators are awesome in that they dereference like normal iterators. So if you actually notice in the all of example, where we're passing in iterators here, is actually doing a dereference right here. Right here in this part is just doing a check whether the two iterators are at the same, they're pointing to the same location. But this right here, we're actually looking at the actual value corresponding to the iterator, the thing that the iterator is pointing to, namely the value inside the, say, vector. We can advance pointers along, and we can back up the pointer if it's a bidirectional iterator. In this case, all three iterator types are this one. So the begin iterator corresponds to the begin of the vector, and the end points to past the end. And so it should never be dereferenced that way, which is actually why it's never dereferenced here. So if first becomes the last at any point by increment here, it'll become equal to last, and so therefore we exit the loop, and we don't do a dereference here, which is nice. Okay, a few more slides. Traversing containers. So I wouldn't actually do this. So this is just one way you can access. We can traverse an iterator using an iterator. One way that we learned that is much better is using the range-based for loop. But if you don't use the range-based for loop, you can actually use, say, the find function in the standard library. So here, it's actually taking two iterators here, and two input iterators. So these are just general iterators here, and a corresponding value, and it's just looking for the value. So if we're, say, looking for a value, it's not really looking for one here. But if we're looking for a value, don't write code like this. Just call the find function easily like this. So we can just call the find function with the begin of the, in this case, the array, but for vectors we call .begin, and then we call .end on the vector here, and then the value that we want, which is far easier than writing code like this, and less error prone. There are other algorithms in the standard library. So binary search, there's one built in. There's, and we talked about that before. For each, so if we wanted to do some operation on each of the values in, say, a vector, that we can call for each, and then pass in a what is it? A function object or a lambda corresponding to what you should do for each of those elements. Max element will return to you an iterator corresponding to the maximum element. Random shuffle, there's actually a better function now called shuffle, not the random, for other reasons, but that will shuffle all of the elements in the, say, vector completely arbitrarily randomly. So if you wanted to shuffle all the elements around, just call that function. If you want to find the number of some element in the vector, then you call count. If you want to find an element, you call find. If you want to find the minimum element, you call min element. And sort we have seen before. So some of these, so like binary search returns true or false. For each doesn't return anything because we're just doing the operation on the value. We don't need to return anything. Max element and min element actually return to you an iterator, so you have to do a dereference in those cases if you want to actually find what the value is of the maximum element. Shuffle doesn't return anything. Sort doesn't return anything. Find, I'm not actually sure. I think find returns to you an iterator. So let's actually look at this. Yeah, so find returns an iterator. So like for min and max element, you need to do a dereference there. Count returns an integer because, maybe not exactly an integer, but it's like an integer, where you, because it always, the number of something in a container is always an integer, so it returns an integer for that reason. But you have to include the algorithm header file for these. And of course, as we've seen, that there are way more other functions. So like something called stable sort, partial sort, nth element, many other things here, a lot of other functions. Yeah, so these are the ones that we actually talked about before. And I think we, so that's actually all the slides. And I think we are out of time. We're actually really close to it. So thank you all. I'll see you all on Friday.